All right, thank you very much for having me. My name is Mike Place. I come from Salt Lake City, Utah in the United States. I am so happy to be back in Munich. I really appreciate the very kind invitation to come here and spend a morning with you all. I work for a company called SaltStack. I am the principal project maintainer of the SaltStack project. For those of you that do not know Salt is a automation framework primarily built for large-scale deployments, but handles all sorts of things from IoT to embedded to managing routers and switches to managing large data centers and on and on and on and on. Salt is one of the largest and most active open source projects in the world. To give you an idea of what that looks like, that means that on a typical week in Salt, we merge anywhere from between 5,000 and 10,000 lines of code. We move through usually about 1 million lines of code merged every 8 months. And things stay very, very, very busy. And by that I mean through all the branches, because the math doesn't add up there. At any rate, you can find me at mikeplace.io and nowhere else on the internet, because I am not on social media, because I believe it is out to destroy the world. Before I begin, I want to, as I do in all of my talks, thank these gentlemen. For those of you who don't know, this is Luke from Puppet, Mark, the inventor of CF Engine, and Adam, the inventor of Jeff. Though we compete, I have tremendous respect for all three of these gentlemen who I think are pioneering thinkers in the automation space. And I hope that if you look at Salt, if you look at our project, that you'll certainly look at the other projects as well, because they're tremendous projects and tremendous human beings. This talk is about principles over products. I know many times we go to conferences and we sit in talks and we learn about specific types of tooling. And if that is the talk that you're looking for, this is not going to be it. Because I believe in talking not about specific products and specific sets of tooling, but about design principles that we can use to inform the way we build our networks, the way that we lay out our automation, and the way that we do our day-to-day work. And so as we go through this talk, you're going to see a little bit of code. You're not really going to see any type of specific product, Salt included. But it's my hope that you can look at these principles and that you can apply them in your day-to-day work, no matter what tool it is that you end up using. Part one. So the future, I think, is a distributed system with a convergence problem. And what do I mean by that? I mean, so often people think that automation is all about greenfields, right? But it's not. Everywhere I go, people say, okay, look, here's my automation problem. I say, cool, let's start talking about it. And they say, I've got Linux over here, and I've got a mainframe system over here, and by the way, I've got 3,000 switches over here, and 200 of them haven't been upgraded since 2015, and there's a whole AIX deployment, and oh my goodness, right? So when we think about automation, I think that it's important to remember we're always operating in a hybrid context. The first question that I want to pose to people today is, to ask ourselves, how do we reason about the complexity of the systems that we're building? One of the things that interests me very much is a scientific field called complexity theory. And when you look at complexity theory, many of the researchers say, well, there are 3 things we can look at to reason about how complex a particular network is. 1 is the number of nodes. 2 is the interconnectivity of those nodes. And 3 is the tendency to fail on any of those connections. And what we've had to do in order to reason about all of this complexity is we've had to build layer upon layer of abstraction. A lot of times you hear people say, well, you know, simple is best, right? Whatever is the simplest thing is the best thing. And I think that while that's a really tempting and wonderful thing to believe, we must also always think about whether or not we're actually talking about a reduction in complexity or whether we're talking about an increase in abstraction, because those are two very, very different things. And if we don't think carefully about those differences, we're going to start to build networks that we can no longer reason about. And in fact, I think we are very nearly there. So one way we reason about these complex networks is through the idea of patterns, through design patterns. We think about design patterns a lot in software. If you have a CS degree, you've surely sat in classes and you've learned about various programming design patterns. But how often do we think about infrastructure design patterns? Hardly at all, right? So the claim that I want to make, and the case that I want to lay out today, is that active humans building proactive processes end up building reactive systems. What do I mean by that? I mean, when we think about the way that these complex networks are laid out, we have to think not just how is the application going to operate in this space, but how are we going to be proactive about failure, right? Because we're very good at building systems that say, hey, if X happens, then do Y, right? That's what sort of like application and infrastructure design is about. But we're really, really bad at building systems that say, if not X, then Y, right? Why? Because it's a harder problem, right? Because the measure of things that you have to account for becomes greater and greater and greater and greater. So how do we do this? So new ideas are hard to come by. I want to always take us a step back and think about the history of where we've come from, whether it's in automation or in distributed computing. I think distributed computing has three pillars. The first, the ability for the system to be aware of the existence and capability of its member nodes, right? When you read like the marketing literature, right, this is called, service discovery. The ability to coordinate tasks between those nodes, right? Again, when you read the marketing material, this is called, a scheduler. Right? You should know this. These patterns, like, we know about these if you've done kernel design, right? The same principles are being applied at the data center level. Interprocess communication, which can connect nodes in the system to each other. The thing that I want to point out here is that when we look at what modern distributed computing is today, it's the very same level of abstractions, right? The same sets of abstractions that operate on individual operating systems. We simply have moved higher up the stack, right? Now, the fundamental unit of distributed computing I want to argue today is what I call the event. What is an event? Well, an event is exactly what it sounds like. An event is a thing that happens on a network, right? A thing that emits a log entry, a connection to an API endpoint, a system that goes up or down, a system that has load of X, right? A system that loses disk Y, and on and on and on and on. As we build out these complex networks, we have all of these events that are happening. But what do we do with them? The next thing that I want to talk about is a message bus, right? Because the fundamental point that I want to make today as we start to talk about what event-driven infrastructure looks like is that we can take all of those events, all of those things that are happening, and we can distribute them to consumers who can then listen and decide how to react. So a message bus is simply the distribution medium for events on a network, right? Sometimes you call this this message-oriented middleware. To build a message bus, you have to have a data model, right? A way to describe and frame the messages that flow across this bus. You have to have a command set, a way to operate on these messages, all right? You need to have both a physical and a programmatic transport for these messages. But the question that I now want to ask is, okay, cool, that's sort of the technical explanation of what a message bus is. Now let's take a step back and look at the way our teams are organized. So if you think about a message bus, what would a message bus look like for an operations group, for example? Right? We do have message buses, right, in areas like monitoring. Right? We have message buses in areas like configuration management. We have things called chat ops. We do auto scaling. We have serverless, right? So I want to pause on serverless for just a second and return you to this idea of modern infrastructure really being event-based. If you look at serverless, serverless fundamentally operates on the principle of the event, right? If you've ever used AWS Lambda, you see this, right? Events flow in through functions, right? And are connected to external services like RDS or whatever through an event-based architecture. We're seeing this pattern emerge more and more and more. You might see provisioning as a message bus for ops, so on and so forth. Now, what do message buses look like for developers? Pretty much anything that connects these various layers of this application stack has a message bus of some kind. Sometimes these are streaming, like streaming's APIs, and sometimes they're set up and they're torn down on demand, so on and so forth. So the question that I want to ask is, what sorts of possibilities emerge when these siloed streams of events become shared with each other, right? What happens if we merge those two silos together? If we merge the event-oriented nature of the applications we build with the event-oriented nature of the infrastructure that is running underneath it, what sorts of things can we do? So let's ask ourselves, what does most automation look like right now, right? So I build automation software for a living, and really, I think we've got a long way to go because most automation software right now is just repackaged workflows. Right? That's all it is, right? In some cases, it's procedural and it's remote execution oriented. In other cases, it's idempotent and state-based, but still, they're packaged workflows, right? We sit at our little terminal and we say, okay, now we're going to do apply state X, right, to sets of machines Y and Z. All right, we take the series of steps, we list them out, and hopefully things go fine. But most of the time, the issue is that when we talk about automation, we're still talking about these packaged workflows that are just initiated by lazy humans. We're not talking about what I would call automation with a capital A, which is automation that exists and is inherent as a first-class citizen on the network itself. Automation that can hear what's happening on the network, gain a contextual understanding of what is going on, and then automate based on that understanding. Right? Now, the problem with, or one of the big problems with automation right now is that it still becomes very brittle, right? And one of the reasons that automation is really brittle is because we, right, as humans, are constantly chasing the state of our systems. If you go and you listen to any talk by Mark Burgess, which you absolutely should listen to everything he's ever said out loud in public ever, he talks about this really, really wonderfully, right? We're sort of chasing the state of our systems, right? And because our systems are always changing out from underneath us, right? The automation that sits on top has to match, and if it doesn't match, it oftentimes becomes brittle or breaks. Now, all of this doesn't feel very much like programming, right? And I think whether you think this is awesome or not says a lot about you and a lot about us. So let's turn now to principles of event-driven programming. If there are programmers in the room, you know what this is like. God forbid that I would say this at an automation conference, but if you've ever done any JavaScript programming, you kind of know what event-driven programming looks like. It's this paradigm where the flow of the program is determined by kind of these asynchronous events, right? Whether it's sensor outputs or mouse clicks or key presses. If you've ever written an iPhone application, you know all about this, right? It's this dominant paradigm that's often used in graphical user interfaces, for example. Like I said, JavaScript, Node.js, GUI applications, iOS, so on and so forth, right? So there are three principles of event-driven programming that I want us to think about as we start to understand the principles and think about how we might apply those to automation workflows and to the way we build and manage our infrastructure. So these three principles are, number one, a set of functions which can handle events. Well, that's pretty straightforward. Two, a mechanism for binding these registered functions to those events, right? If X, do Y, right? And a loop which constantly polls for those new events and calls these matching event handlers when one of those registered events is received. So there are some criticisms of event-driven programming. On the one hand, there's this notion of imperative programming, right? That we can, write procedures to perform these steps, in a given order. And on the other hand, we have this idea of declarative programming, right? That we can declare the intended state of a system without explicitly describing the steps that it takes to achieve that state. This is, by the way, a kind of an old and unfortunately kind of still ongoing debate in the automation space. Additional criticisms of event-driven programming. Highly asynchronous code, right? And event-driven programming is asynchronous. That's a fundamental property of it. Highly asynchronous code can be difficult at times to troubleshoot. And it takes a little bit of a mind shift to think about imperative and declarative approaches melded into one, which is really what this looks like. And I think it can be challenging to translate these procedural workflows into something that is event-driven. But there are advantages. I think it's easy to find natural dividing lines for unit testing infrastructure if we think about things in this way. All right? It's highly, highly, highly composable. All right? Now let's pause here and return to this question that we asked ourselves about reasoning about complexity. Right? One of the ways that I think we're doing this that is really interesting to me is as we started out in this DevOps movement in 2008, right, with John Allspaw getting up and giving this wonderful talk. I was there. I like to talk about how I got to see that talk in person. It was fantastic. But he gets up and he says, look, here's the problem that we're trying to solve at Flickr, right? The problem is, we want to be able to do multiple deploys a day. And everyone said, oh my God, you can't do that. That's impossible. And he said, no, we can, right? Cool. This is how we're going to do it. And he said, we need to bring our dev and ops teams together, right? And we need to, fundamentally what he was saying was, we need to build not just a cultural bridge between these teams, but a linguistic bridge between these teams as well, right? Because we need to give them a shared language to use to describe the infrastructure that they're operating upon. Well, that's really wonderful and really neat. And we went on doing that, and DevOps sort of emerged into this cultural phenomenon. But something really interesting happened in technology while all of that was going on, right? Which is that the principles of composability and abstraction continued to move forward, right? If you look at something like Kubernetes, for example, reapply that to the problem that John was trying to solve, right? All of a sudden, we've built software, right, that doesn't connect those two teams anymore, right? It re-abstracts them back away from each other, which is really, really interesting. That was a bit of a divergence on my main point, but anyway. Additional advantages, both approaches get a little bit brittle as they grow in length, but it's a good way to model systems that need to be both asynchronous and reactive. So high-speed event bus, right, plus event-driven programming gives us event-driven infrastructure, all right? So I'm going to skip ahead a little bit because I'm getting a little low on time. What are the principles of event-driven automation? One, events originate from applications and from systems and are transmitted across a bus, all right? Very much in the same way, I like to think of this as the same way that Ethernet works, right? When you look at layer 2 in the OSI model, think about how that operates, right? You have broadcasts that are coming in, and machines know, oh, does this apply? Is this something that I care about, right? If no, fine, cool, no problem. But if it is, then do something, right? Mechanisms in event-driven automation exist to sort these events and apply rules to them, all right? And as these rules are matched, these registered actions occur and promises are met. There's some disadvantages here. There's potentially tight coupling between the event schema and the consumer of the schema. Message loss is potentially a problem. And I think one of the most troubling things is that I think it's still really hard in this model to reason about what blocking operations should look like in a highly asynchronous environment. Testing, of course, always a little bit tricky. What are the advantages here? The advantage is that we can build distributed, scalable, but most importantly, loosely coupled systems, right? Because if we can move away from this model where we have to have service discovery so that we can connect endpoint to endpoint to endpoint to endpoint to endpoint to endpoint to endpoint, right? That's not going to get us where we need to go over time. Where we need to go over time is saying, okay, all right, application pod, whatever you are, here are the things that you need to be responsible for, right? Just like a cell operates in the human body, right? If you hear about thing X, right, here are some things that you can do about it, right? If you hear about application degradation, here are some ways in which you might be able to account for that, right? We need a DevOps automation backplane for a system, right? Because, again, we need to connect these disparate groups, right? But ultimately, automation needs to do more than simply be focused on the life cycle of any given machine. And it's unfortunate to me that so much of the talk about how automation operates, right, whether it's in the container space or in the cloud space or whatever, is focused just on the first 30 seconds of what a machine looks like. Right? Because often you hear two cases being made. One is, hey, cool, I can, take machine image X and I can make it into Y, and then I throw it out in the universe and everything will be fine because nothing ever changes in the world. Cool, right? But hey, if something does change, yeah, no problem. I'll just go out and patch it. Cool. Like, that's a fine story. But I think what real automation should look like is a first-class citizen that can operate moment to moment, that can interface both with the infrastructure that it's living upon and the application that is living upon that, right? And in doing so, it provides this immediate common programmable layer on top of deployment systems. So fine, how do we build one, okay? First, we have a flow. An event is emitted onto this event bus, right? It flows to a manager. A manager checks to see if this event matches a registered handler. And if so, we can check a series of rules. And for each set of rules that are matched, some action is undertaken, right? So what are the moving pieces that we need to do this? And I apologize, I'm moving a little bit quickly, but I'm a bit behind on time. We need an event bus transport, right? We need some way to fire some sort of automation middle layer or middleware to fire all these events around, right? So we need a transport. We need telemetry, right? Something to emit these events, right? Whether it's from the application or whether it's from the infrastructure itself. We need actors, right? That are the machines, the things that are emitting these events, right? And we need reactors, right? Processes to ingest these events and act upon them, right? So how do we build one of these event buses, right? Event buses must handle security and reliability and serialization, and it may handle, easy sets of interfaces and message filtering and message routing. All right, message bus topology. Generally pub-sub, right, which is one-to-many. The good news here is that we have really, really good systems for doing this right now, really good systems that you can pick up off the shelf, all right? Salt, my project, uses ZeroMQ, which is terrific and amazing, but of course you have other options like Kafka or what have you, all right? So you could go pub-sub. You can also build a push-pull or a fan-out or whatever it is that you need. As I mentioned, tons of off-the-shelf messaging here. Often the off-the-shelf messaging gets used simply to connect these application layers together, right? But remember that the point here is not just to connect the application, but to connect the application downward to the infrastructure, right? To imagine what would happen if the infrastructure itself could participate in that bus. We need telemetry, right? Light and easy software that our application developers can use to emit events onto this bus, right? It should be really lightweight, so on and so forth. And so I'm not going to walk you through a bunch of code. I'll put these slides up online and you can check it out. But here is something like that in Python, right? Just incredibly easy. All you have to do is basically create a tag, start to spin up a socket, and then start to push events onto the socket. The point of this is that we have really, really good messaging and eventing frameworks right now that are really easy. Reactors fundamentally are just decision engines, right? They register events that occur, and then they perform actions when they need to be performed. They can be as simple as they can be as complex as one wants. But the idea here is that we can create a shared abstraction for these rules. So, here is an idea of what an event bus is. This is not any particular tool. It's not Salt. It's anything else. It's just some genericized YAML that says, okay, here's the way we could describe, right, the structure of this workflow. Here, if we receive, right, something that matches this client load tag, we could fire certain reactions. We could register the fact that we received this event onto a register that might do things like count or average over time or what have you, and then we can apply some rules. Simple. That's event-driven infrastructure right there. All right. I'm going to skip over actors really quick. All right. So finally, I would be remiss if I came all the way over here and didn't talk a little bit about tools, right? Salt, which you can take a look at saltstack.org, really tries to embody these principles, right? It tries to embody the principles of automation as a first-class citizen, of event-based programming, highly asynchronous, and highly performant automation. We believe that configuration management is not a tool, but configuration management is a service that rides upon a generalized automation framework. To us, that's a really, really important difference. You can see here, this is just a slide I put in that sort of shows our topology. We have what we call a master-minion relationship, right? So we have these masters that can send events down to these minions. We have minions that can emit events upward to masters, and we have a shared bus. And then on either the masters or on the minions, we have what are called reactors that can listen to these events and then perform actions as they are received. Those actions can be, again, translated or moved into the configuration management layer to perform actions. They can be moved into the cloud management layer to provision machines, whatever it is. All right. So I'll skip over this stuff simply because it's a little bit too long. So finally, what I want to show you real quick in just the last couple of minutes is sort of a real-world example of how this looks. This is something that comes from our friends at Cloudflare. All right? Cloudflare actually uses Salt as sort of the muscle for their DDoS protection. Right? It's part of the way they've done that. And so what they've done is they said, okay, look, as events come in, right? We know what events look like, in a DDoS scenario. We're going to register those events, and if we receive something, right, or if we receive something that says, oh my goodness, this particular event has gone down, or this particular interface has gone down, right? Then what do? Okay, if we receive that, then we shut some stuff down, we send some email, we figure out what corrective actions we might need to take, and we're off to the races, right? So this is simply a reactor that says, okay, if you receive this type of event, here are the things that you need to do, and here's a description of those states, those things that are being launched when the reaction happens, all right? Anyway, you can look here, and again, these slides will be up online. The first is the first link that you see here is some genericized code. It doesn't have anything to do with Salt or anything else. That just tries to show, both in pseudocode and in text, some of the principles that I've spoken about today. The second is a link to a presentation by Mircea, who works at Cloudflare, if you want to see a real-world example of how they use event-driven automation to respond and correct for events happening on their network. So in review, in the last few minutes I have, to build scalable systems, we need to adopt the lessons of distributed computing, because we can migrate from these simple human-initiated workflows to reactive, programmable systems. We can do this, and event buses are pretty good, so let's build some more of those. Right? And finally, we can build and we can apply these patterns on top of existing tools. We don't have to build, thankfully, this stuff from the ground up, because it does take some work. But we can build on top of tools like Salt that give us this full automation toolkit that can operate up and down the stack. So with that, see, I have 50 seconds left. I will happily take a couple of questions if I have time. Yeah, okay. 5 minutes of questions, okay. So if there are questions, I'm happy to try to take them.